Welcome to the Hughes Communications Lab of the University of Maryland at College Park. I'm Alejandra Mercado. I'm Associate Director for the Masters in Telecommunications program at the University of Maryland at College Park. I'm also an instructor, a mentor, an administrator, and a lab coach. The Hughes Lab provides hands-on experience where students learn to work with the ETIS B210 software-defined radio, as well as the GNU Radio Companion, which is a front end to the GNU Radio libraries for digital communications and signal processing. Let's first see what an AM signal looks like. First of all, we have M of T, our information bearing signal. And that could be music, it's going to be baseband, not yet upconverted to the carrier frequency, and it can be anything we want. Let's say it could be a bandwidth of 20 kilohertz or less or more. Then we have the carrier wave. The carrier wave is an empty vessel used to upconvert our information-bearing signal to the higher carrier frequency. And in our case, it's going to be a cosine. So it's going to be some amplitude, AC, we can set it to 1, times the cosine of 2 pi times the carrier frequency, T. Now, our amplitude modulating signal, which carries our information signal M of T using the carrier signal C of T, is going to have this form. It's going to have the amplitude of the carrier times 1 plus the amplitude sensitivity multiplied by the information bearing signal, the music or whatever, times the cosine. Here we see the information bearing signal. It's an example in the time domain. So it has a certain rate of change that will be reflected if we were to see the spectrum of this signal, and its maximum frequency content would reflect how quickly this signal can change. Here we see both the information bearing signal and the empty carrier. The information bearing signal we saw before in blue, the empty carrier in red. We're going to need to zoom in to see more detail so we can talk about the relationship between the carrier frequency FC and the information bearing signal. As we zoom in, we can see more detail of the carrier, the red carrier at the bottom. So you can see its frequency is about 500. It moves, it changes much faster than the information bearing signal M of T. And we're going to rely on that because the information bearing signal has to be carried over the envelope of the AM signal. What we're seeing now is the information bearing signal in blue and the AM modulated signal in black beneath it. In order to see more clearly how the blue signal affects the black signal, we're going to zoom in again. Now that we've zoomed in, we can see more clearly that the blue information bearing signal is shaping the envelope of the AM modulated signal. Wherever you see a trough in the information bearing signal, you see a trough in the same position in the envelope. Wherever you see a peak in the information bearing signal, you see a peak in the envelope. As a matter of fact, the fact that the envelope of the AM signal is being guided by the shape of the information bearing signal will allow the receiver to use an envelope detector in order to recover the information bearing signal. Let's say that our AM signal called SAM of T is being propagated, being broadcast over the airwaves along with other signals that are using different carrier frequencies. So SAM is our AM modulated signal, where M of t is the desired signal that we wish to recover at the receiver. The out-of-bound signals can be anything, Lady Gaga, Led Zeppelin, anything else that we don't want to at the receiver. Another thing that gets added to the desired signal is the additive white Gaussian noise at the receiver. Now, this additive white Gaussian noise, we call it white because its power spectral density is a constant. In this case, its power spectral density is n0/2, a constant over all frequencies. All of this added together arrives to the receiver and is fed through a band pass filter. And the band pass filter is designed explicitly to allow SAM through and to block the Y of t and the Z of t. The other thing that happens is that the noise, which was white before going through the band pass filter, is now colored. So it's no longer W of t, it's N of t. The filter is designed not to alter or change or mitigate the SAM desired signal. And now the noise has gone from being white to narrowband noise because of the bandpass filter. So what's coming out of the bandpass filter, let's call it X of t, is our AM signal, which is 1 plus Ka, that's the amplitude sensitivity, times our information bearing signal M of t, times the carrier cosine 2 pi FCT. And the narrowband noise, we can, now that it's narrowband, we can write it in terms of its in phase and its quadrature components. And as you can see, Ni, it's its in phase, and Nq is its quadrature components. We can group everything that's multiplying the cosine together and everything that's multiplying the sine in another group. So we get all of the in phase components of X and all of the quadrature of X as well. The in-phase part is the part that multiplies the cosine. The quadrature is the part that multiplies the sine. Now, so far we have X of t, which is going to be fed into the envelope detector at the receiver. An analog envelope detector will be a diode and a capacitor in parallel with a resistor. But for our software-defined radio, it's probably going to be a digital analog detector, which simply means taking the absolute value of the different samples and then passing them through a low-pass filter. The output of the envelope detector will be the envelope of X of t. And we know that the envelope of X of t, we studied it together in Chapter 2, is the square root of the in-phase squared plus the quadrature squared. We know what these components are. We have them just above there. The in-phase squared is going to be AC plus ACKA M of t plus NI quantity squared. And the quadrature is going to be NQ quantity squared. Now, in order to simplify this, we're going to have to make some assumptions. If we assume that the in-phase component is much, much larger than the quadrature component, then the term inside of the square root simplifies. Y of t, the output, becomes the square root of the in-phase term squared, which in itself just becomes AC, which is known, plus ACKA times M of t. AC and Ka are known. M of t is the information bearing signal that we seek, and Ni would be the noise term at this point. With the assumption that the in-phase term is much larger than the quadrature term, then and only then the output will be equal to a DC term plus a constant times the information bearing signal that we seek plus a noise term. The AM threshold effect tells us that below a certain carrier to noise ratio, in other words, if the carrier is much weaker than the noise, then the envelope detector stops yielding this approximation of a constant times m of t, and the AM receiver stops working. We're going to see that in our example. Once again, we're going to use our inexpensive NOAELEC Mini SDR. Its frequency range, which means the frequency range for which it functions properly as a receiver, is 25 megahertz to 1.75 gigahertz. And it has real-time bandwidth of up to 500 kilohertz. Now, we've seen this before in video 1 of this video sequence. So if you haven't seen the video number 1 for our sequence, I urge you to go back and watch that one before going on in this one. Therefore, as long as the signal we're trying to receive has a bandwidth that's no bigger than 500 kilohertz and is somewhere between these two frequencies, then we're okay. Now, AM broadcast radio uses 10 kilohertz real-time bandwidth, which is less than 500 kilohertz, so we're in good shape. But AM broadcast radio in the United States uses carriers between 550 kilohertz up to 1.720 megahertz. That's a lot lower than 25 megahertz, which is the lowest frequency which our NOAELEC works on. So we're not going to be able to receive regular AM broadcast radio on our little SDR. On the other hand, if we use citizens band radio, CB radio for short, they also use AM 10 kilohertz real-time bandwidth, which is less than the 500 kilohertz that our NOAELEC SDR can handle, so far so good. And the CB radio uses carriers between 26.965 megahertz up to 27.405 megahertz. And that is within the range that our little NOAELEC works. So we should be able to set up our NOAELEC to receive CB radio. Let's do that now. First we run cubic SDR. If you haven't seen our first video of this series, please pause and watch that one before you view this one. The program will try to find our SDR, and there you'll be able to see RTL2832U device in the list. Click on it to turn on the SDR as a receiver. The Rafael Micro Digital Tuner in the SDR is down-converting the received signal to a low intermediate frequency. Then it samples it and sends the sample to the SDR's Realtek digital demodulator. Here, the cubic SDR shows us the spectrum of all the signals that the antenna received. First, we'll set the bandwidth to 10 kilohertz. Just hover over the bandwidth digits and use the mouse roller. This office is not too close to any large road or highway where truckers may be using CB radio, but we did detect something around CB channel 15, which is 27.135 megahertz. So let's set the center frequency to 27 megahertz. As we saw in video 1 of this series, the default sampling rate of the SDR is well above the minimum 20 kilohertz we need for AM, so we can leave that at the default value. We're ready to instruct the SDR to act as an AM receiver by clicking here. Now we'll search for the CB channel 15 at 27.135 megahertz. We hover the mouse over the carrier we want in the waterfall and click. We use the mouse to adjust the carrier frequency to channel 15. You'll notice that the best centered frequency may not be exactly 27.135 megahertz on the screen. This is because the local oscillator in our little SDR may be drifting slightly from the exact frequency, so we have to search for the signal. Even so, you can barely make out the lady's voice embedded in the noise. The reason is that we are very far, and her signal is very weak. We are, in effect, seeing the AM threshold effect in action. AM transmitters and receivers like envelope detectors, filtering, sampling rate, channel noise, down converting to intermediate frequency IF, local oscillator drift, AM threshold effect, are all some of the topics discussed in digital communications. If you like these subjects, then maybe taking ENTS 622 would be interesting for you. If you really want other electives and you pass the placement exam, then you can still play with other SDRs at home. Here at the Masters in Telecommunications program, we strongly believe that the best student experience involves hands-on labs and projects to equip our graduates to excel in the workplace. One of the things that attracts students to our program is that we are very industry focused. We keep a constant tab on the skills that hiring agents want, and we make sure that we offer courses and labs that provide these skills.